Hello again. Here we're actually going to utilize the chain rule. So in this particular example, I'm going to use the first version of the chain rule from what you saw earlier. So we have y is equal to the quantity of 2x plus 10 raised to 10. Now, if we take a look at this problem, if we sort of pretend that the inside didn't exist, well, this would actually be a very easy derivative because essentially we can just put 10 out in front and then minus 1 from the exponent raised to 9. But we don't have exactly that, but let's change it so it's actually a very easy derivative. It'll be a simple power rule. So let me actually put that back inside. But how I can make this into an easy derivative if I just make a substitution. So let's make u equal to 2x plus 10. Let me actually write that in a different color. So u is equal to 2x plus 10. So y is equal to u raised to 10. So this is actually a very easy derivative if we take it with respect to u. So we'll actually do just that. We'll take d du of this equation. So dy du is equal to, and now the derivative using the power rule will just be 10u raised to 9. So that was pretty simple. However, we want dy dx, not dy du. So again, we'll use our chain rule to get dy dx. We'll just multiply both sides by du dx. Du dx. So you can see in our notation the du's cancel out. We'll have dy dx is equal to 10u raised to 9 times the derivative of u. So let's actually find du dx. So we already said u is equal to 2x plus 10, so we'll simply just take the derivative with respect to x, and this will turn to du dx. And let's see, what is the derivative of 2x plus 10? Well, it will just be 2. This is a linear function. So times du dx. Now all we have to do is just make our substitutions. So we have du dx. Du dx is just 2. And we actually already know what u is. U is 2x plus 10 from earlier. So 10 times u raised to 9, 10 times 2x plus 10, then raised to 9, and then times our derivative of u, which was 2. And that's equal to 20 times 2x plus 10 quantity raised to 9. And that is our derivative of our y function. So the trick here was to use a u substitution, and essentially what the u substitution does is that it turns your hard problem into an easy problem, quite literally just transforming the type of problem we had. We had some sort of composition going on, an inside function raised to a very large number. However, we just changed it to a simple power rule case by making that substitution. So that's definitely one way to use the chain rule. In the next example, you'll see we'll use a different version, and that can also be helpful to you as well. So our next example will use the second version of the chain rule. So that means we'll just use this formula on our right-hand side. So f prime of g of x. So that means we'll take the derivative of the outside function. So let's actually first identify the outside function and the inside function. So a good hint is, having parentheses. What's inside the parentheses is usually your inside function. You have x squared plus 3x. It's a quadratic inside something being cubed. So yeah, you have your thing being cubed, and then you have quadratic. So you have a cubic, a quadratic. This is inside that. The x squared plus 3x is inside the cubed part. So f prime means let's just take the derivative of the outside function of, let's say, x cubed, which would just be 3x squared. So we'll just treat it as such. We'll leave the inside alone. That's what f prime of g of x means. Just leave the inside alone and differentiate how you can. In this case, it's the power rule. Put the 3 up front. Minus 1, we have a 2. But first, we have to multiply by g prime of x. So g prime of x is the inside. So what is the derivative of x squared plus 3x? So g prime of x will just be, again, using the simple power rule, we'll have 2x plus 3. So let's just multiply by exactly that, 2x plus 3. And there, this is our derivative. Let's just clean it up. I'll just distribute the 3. So x squared plus 3 squared times, distributing the 3, we'll have 6x plus 9. And there you have it. This is our cleaner answer as opposed to what we had before. So, and after a while, you'll actually just find this useful. You won't have to do the u substitution all the time, just recognizing the inside function and the outside function. I personally use a mix of both. So let me just rewrite it. So our dy dx. And what do I mean by both? I'll just put in u for g of x as opposed to g of x. So f prime of u times u prime. So very easy to write. Let's just define our inside function and our outside function. Our u will always denote the inside function. So let's just take a look of what we're dealing with here. So root 4x minus 6. So we can sort of establish that we have a big radical going on here. So we'll say our outside function is the square root. And then our inside function will be 4x minus 6. So let's just write that our inside function, is 4x minus 6. And now let's just follow the format of the formula. So f prime of u, so let's take the derivative as if it wasn't anything important inside. So let's just rewrite the radical as raised to 1/2. And let's take that derivative. So 1/2 comes up front. We still have the 4x minus 6. And then minusing 1/2 minus 1 will be negative 1/2. All right, almost there. We just have to multiply by u prime. So we have u here. So u prime, the derivative of 4x minus 6 will just be 4. Now let's just multiply that there, times 4. Okay, so that is our derivative. The calculus portion is done. Let's just simplify. We have a 4 times a half. Let's do that. It'll be 2 times 4x minus 6 raised to negative a half. And let's just flip that. So 2 over 4x minus 6 raised to a half. And let me actually put a radical as opposed to the half. So we'll have 2 over radical 4x minus 6. And that's our final answer. And just recognize your u, what your inside function is. Take the derivative of the outside function as normal. And then just to finish it off, multiply by your u prime, your derivative of the inside function. Another example, I'll identify our outside function, which looks to be something raised to negative 3 times 5. And then we'll identify our inside function, which is actually inside the parentheses. So, which is our u. Our u is 7x cubed plus 1. So let's just take the derivative of u, find our u prime, and this will actually turn into 21x squared using the power rule. So let's just apply our chain rule. So the outside function, let's just take the derivative and ignore everything inside. So we'll get negative 15 times 7x cubed plus 1, and then minus 1 from the exponent, so raised to negative 4. And then finish it off, we'll just multiply by our u prime, which we said was 21x squared. So negative 15, 7x cubed plus 1 raised to negative 4 times 21x squared. Now let's just multiply what we can, the negative 15 and 24. So we'll get negative 315 x squared times 7x cubed plus 1 quantity raised to negative 4. And if we want to clean up the notation a bit, we'll have the negative 315x squared in numerator, bring down the negative denominator. 7x cubed plus 1 raised to positive 4. And that's our final answer. Now this is a bit of a tougher example because we might have to use the chain rule twice. And you'll actually see what I mean in a moment. So let's just pretend this is a normal problem. We'll see our outside function and our inside function. So I see a radical containing a lot of things inside. So we'll just say our radical is our outside function. So it's some quantity raised to 1/2. And our inside function, our u, we'll say is 3x minus 4 quantity squared plus 3x. All right, so first I'm going to take the derivative of the outside function. So, and this is our outside function. So 1/2, leave the inside in there. Don't touch it. So that'll be 3x minus 4 squared plus 3x. And then we have the minus 1. So 1/2 minus 1, that's negative 1/2. And then to finish it off, we need to multiply by our u prime. So let's actually find our u prime. So we'll take the derivative, u prime, and we actually sort of run into a situation where we need to use the chain rule again. Because as you can see in this first term, we have some quantity being squared. So some quantity being squared. And then we have an inside function, which is a 3x minus 4. So let's just focus taking the derivative of that piece first. So take the derivative of the outside, ignoring everything in the inside. 2, 3x minus 4. 2 minus 1 is 1. So that's our derivative. And then times the derivative of the inside, or u prime, or since we've already used u, we can say just our inside prime or v prime. But let's not use too many variables. Let's just focus the derivative of the inside of this function, which is 3. 3x minus 4, the derivative is 3. And that's the derivative of the first term. So let me just match it up here. That's the derivative of the first term. And we still have our other term here, the plus 3x. We just have to differentiate that. And that's an easy derivative. That's just a plus 3. And let's actually clean this up. We have a 2 times a 3. So this will be 6 times 6x, 3x minus 4 plus 3. And let's distribute and combine like terms wherever we can. So this turns to 18x minus 24 plus 3, which will turn to 18x minus 21. So that's our u prime. Aside, we had to use another chain rule. Besides that, we go back to our original problem. And now we have 1/2 3x minus 4 quantity squared plus 3x times u prime, which is 18x minus 21. So let's see. Oh, I forgot to write the -1/2 right here. So let me rewrite this. I'm actually going to move this whole -1/2 quantity to the denominator. So 1 over 2. And then instead of a positive 1/2, I'm going to just put a radical. 3x minus 4 quantity squared plus 3x. And the times 18x minus 21. Which we can just put that entirely on the numerator. Okay, we're 2 here, radical 3x plus 1 quantity squared plus 3x. It's under the same radical there. And that's our final answer. This one just requires the use of the chain rule twice, because it so happened our u in the beginning, to find that derivative, you need the chain rule. So that's it for the basic examples. In the next video, we'll have more complicated examples.